Okay, today we're going to look at dividing radicals. Um, and at the end of this lesson, you should be able to tell me or someone else why we have to rationalize the denominator and how do we do it. Okay, so the first thing we have here is the quotient property of radicals. And the quotient property is similar to the product property. And it's just saying that if we are dividing two radicals, we can put them together underneath the same radical sign. Or if they're underneath the same radical sign, we could separate it into two individual radical signs. Okay, that's all that that's saying. So let's look at a bunch of examples. Okay, so here we have the square root of 30 divided by the square root of 6. And so what I want us to do here is I want us to simplify this first. I want us to actually do some dividing. Both of these are radicands. And so our quotient property is saying that we can go ahead and divide these. It might make more sense to put them underneath the same radical sign. Okay, but we can actually divide those. So 30 divided by 6 is 5. The square root of 5. So if you can reduce the fraction, if it can be reduced, if it can be evenly divided, then you should reduce the fraction first. It will make it a lot easier. Okay, so let's talk about here now. We're going to add this next piece, rationalizing the denominator. And so I want us to look at this example first. Okay, so square root of 12 divided by the square root of 5. Now, they don't divide evenly. They don't have any common factors. So we can't reduce anything. And we may see that the square root of 12 has some perfect squares in it. So if you wanted to pull out those perfect squares first, you could absolutely do that. But I'm going to suggest that we're going to rationalize the denominator first. And so I just want to remind us about what simplest radical form means. We can have no perfect squares other than the 1 in the radicand. We can have no fractions under the radical sign. So here when we have the square root of 30 over 6, that would be an example of a fraction underneath the radical sign. We can't have that. That's not simplified. And then the third one is we cannot have any radicals in the denominator. Okay, so if you'll see right here, square root of 5 is in the denominator. So I've got to get it out of there. And so we have to think about what could I multiply by so that it was only 5. And we have to think about too that whatever, since it's a fraction, whatever we do to the bottom, we also have to do to the top. Whatever we do to the denominator, we do the exact same thing. So a lot of people tell me here to square it. Well, squaring the square root of 5 is not the same thing as squaring the square root of 12, because squaring means multiplying it by itself. So if I multiply by the square root of 5, what does the square root of 5 times the square root of 5 give me? It gives me the square root of 25, which is what? And I hope you're thinking 5. So by multiplying it by itself, it just gives us the radicand. And I kind of showed you the long way of why. Now, if I multiply the denominator by the square root of 5, I also have to multiply the numerator. So that's what I meant by we have to do the same exact thing. So this would be the square root of 60 over 5. Okay, now, does 60 have any perfect squares in it? It sure does. It has 4 in it. It would be 4 times 15. So that would reduce to 2 the square root of 15 over 5. And that's it. That's all we can do. We can't simplify 15 and 5 because one is a radicand and one is not. Okay, so let's write this down. To rationalize the denominator, that basically means we need to get the radical out of the denominator. Okay, and the way we do that is we multiply by the radical in the denominator. Multiply by itself. We only have to worry about the radical. If there's a coefficient out there, we don't need to multiply by the coefficient. And I think I have an example like that in just a second. Okay, so make sure you get that written down. Okay, the next example, square root of 3 over 13. Okay, 3 over 13 doesn't reduce, doesn't divide evenly. So what I'm going to suggest then is maybe we separate it. I think it'll make a lot more sense to look at if we separate it. Okay, so our next problem is we have a radical in the denominator. So to rationalize it, we multiply by the radical that's in the denominator. And both the numerator and the denominator get multiplied by the square root of 13. Okay, so on top, we're going to multiply 3 times 13, both radicands, so we get the square root of 39 over what? If we multiply this together, we're creating a perfect square, or a pair of 13s. Okay, now remember, this cannot be reduced. Radicand, not a radicand. Inside the radical, outside the radical. So this is it. 39 doesn't have any perfect squares in it. Okay, let's look at the next one. We're getting a little more complicated. Remember, lots of different ways you can do this, but if you can do some reducing of fractions first, do that. So everything here could be reduced with stuff down here. Okay, we could put it under the same radical sign. We can leave it separated. We can still reduce it. 3 and 5, nothing happens to it. X squared and x, we can reduce those, dividing. This x is going to cancel out, and I'm going to be left with 1 on top. My y's completely cancel out. So let's write what we have left. The square root of 3x over 4 the square root of 5. Now, doesn't that look a little bit less scary? It does to me. Okay, so we still have a radical in the denominator, so we need to take care of that. Remember, you only have to multiply by the radical, not the 4, just the radical part. So I'm only going to multiply by the square root of 5. Okay. And so let's see, on top, that gives me the square root of 15x. Okay, now on bottom, a little bit trickier. This pair of 5s comes out, and the 4 is already there. So that's going to be 4 times 5, which is 20. And that's it. That's all we can do. Those don't reduce. This is inside, this is outside. Radicand, not a radicand. So we cannot reduce that anymore. Okay, one more. Okay, a little bit harder. And we are dividing two fractions. Lots of different places we can start first, but I want to remind you, when we divide fractions, we have to change this to multiplication, and we have to flip this. So I want us to go ahead and rewrite the problem, changing this to multiplication and flipping it. Now, just like when we do fractions, we can simplify up and down. We can simplify diagonally. So you're probably seeing lots and lots of things that can be reduced. I would definitely probably start with 24 and 50. Okay, 4 doesn't go into 50. 2 goes into both of those, right? I think that's it. So this would become 6. This would become 25, yes? 25 Okay. You may see some more simplifying that you can do. You may stop there. It just kind of depends. It's totally up to you and what you wanted to do. If you wanted to stop there, then we would multiply straight across. But I'm looking at 25 and 27, and I'm thinking, I don't want to multiply those. 6 and 27, what goes into both of those? Hopefully you're thinking 3. So this would become 2. This would become 9. Okay, so look, this makes our problem so much easier. What is the square root of 25? 5. Square root of 8 over, what is the square root of 9? 3. So see, now I don't even have radicals. And so I feel like I've messed up. I think I have. Mrs. Adams has messed up somewhere. And I'm going to have to go back and do this whole video again. So what did I do? Oh, darn. This isn't 6 because I did 2 into it, right? So it should have been 12. I could still do 3 here. It's just going to be 4 instead. Okay, so this is going to be 2. Okay, I apologize. We're fixed, I think. Yeah, we're fixed. Okay, so now I'm just going to multiply straight across. I've got 2 the square root of 8 over 15. 8 has a perfect square in it. 8 factors to 4 times 2, so this comes out. And so now I've got 4, because remember that's the square root of 4, which is 2, times 2. 4 the square root of 2 over 15. I'm going to zoom out a little bit. I'm sorry if I messed you up.